process all the information that came at you yesterday. On that note, I just want to remind everyone that we don't expect everyone to have worked for everything to have worked for everyone. So there's no wrong time to ask a question, even if it's about something we covered the first day. We're going to be here all week. So if you have questions about any of the material, definitely reach out. A couple other things. First of all, to the speakers, you're doing a great job of not touching the screen. So continue that. I guess one of our speakers is going to be remote and doesn't have to worry about that. And then the final thing is that tomorrow afternoon, we will start working on our collaborative projects. And there is a thread in the Slack where some people have started introducing themselves and some of their interests. So obviously, I'd encourage you all to meet each other in person, but also that's a place to start looking for people who might share common interests with whom you could share a group. Okay, so then with that said, I'm very happy to introduce once again Alistair, who will be speaking this morning about parameterizations in MOM6.
Right, thanks, Dan. And this time, just turn that off so we don't have echo. Yeah. You did, good. So this time, this is the scheduled talk, and I presume I was given this title because this is the one I spoke about briefly in the 22 tutorial. That doesn't need to say I'm qualified to talk about any of this. So there's going to be quite a lot of results, equations, theory, and so on, which I'm not going to be able to explain fully, but we'll do what we can. Just a quick correction for yesterday. You remember I had a senior moment and I couldn't remember how you convert the volume integral of a divergence of a flux into the line integral of the flux. And you didn't help me. You do know what the theory is, right? It's Green's theorem, right? You all know Green's theorem. Does anyone not know Green's theorem? Okay, I'm not looking for any hands. Okay, so let's get started. So the ocean is a turbulent fluid. We talked about how it's controlled by the Navier-Stokes fluids and the Navier-Stokes equations, and as somebody said yesterday correctly, they lead to chaotic motions. And our problem with numerical modeling of the ocean is that we're always going to be constrained to using a finite resolution. And that literally always means that there's going to be some unresolved scales below the grid scale. Until you get down to millimeter type or centimeter scales, those unresolved motions will be turbulent. And so we have a requirement in order for the large scale equations to reflect the actual large scale solution that we're looking for. We have to parameterize that subgrid scale, those subgrid scale motions and processes and their interactions with the large scale. So this is the parameterization problem. It's typically known as the closure problem. One thing I like to point out is that, well, first of all, the majority of models, the majority of the code is actually on the right-hand side of the equations. The dynamic equations and dynamical algorithm we talked about yesterday, that's actually a small part. That's effectively, it's not the linear part, but it's almost the mostly linear part, and the well-established part. It's the right-hand side which reflects these parameterizations of what we can't resolve. That is the majority of the code. And you can do that by line count, but it's true for atmospheric models as well. It's all the physics in the atmosphere is the majority of the code. And these parameterizations, the way I like to think of them is that they're actually an encapsulation of all our knowledge about these processes. You basically can't build a parameterization unless you actually understand to some degree that process. And so those parameterizations are usually built from theory and data obtained from laboratory experiments or the field campaigns, or from LES or DNS simulations. I say usually because the theory part of that, which gets us from the data to the equations, is actually today in danger because we can go straight from the data to the parameterizations, and we'll show you an example of that later. So parameterizations. Here's an outline of what we'll be talking about. I'm going to go through these particular parameterizations after explaining where the terms that we have to parameterize appear in the equations. And I have focused on the parameterizations which are relevant, most likely to be relevant for the regional modeling that you're here to do. There's a large body of work that MOM6 has implemented parameterizing mesoscale processes, which you generally will be resolving. So I will include those slides in the notes, but I'm not going to actually have time to talk about them today. As you saw, I tend to go over time, and so this is one way to try and stay on time. And again, the documentation at MOM6 readthedocs.io does have a majority of the material. Okay, so the first thing we want to talk about is Reynolds averaging, which is how we get, or how we traditionally get, to some eddy terms. And the idea here is that you decompose the field that you're trying to model, and that would be temperature, salinity, flow fields, in our case, into a mean part. And it's not necessarily a time mean part, but let's just assume it is for now. A time mean part, and then the turbulent fluctuations from that. And so the field, in this case, field A, which I've labeled A, can be, let's turn on the laser pointer. So this field A, which is a continuous and generally considered to be smooth field, is decomposed into a mean part and then these fluctuations. And we have a property that we use in the Reynolds mean definition, which is that the average, in this case, let's consider a time average, time mean of that perturbation as 0. And that's convenience that makes everything following simpler. So if you look at a product of two fields, A and B, their average, if expanded out, is going to have 4 contributions. But because we're doing an average, we're looking at an average of these two terms here, which have a single perturbation. And because the bar part is constant, that means that these two terms in the middle here drop out. And so you're left with the product of the mean fields and then a correlation between those turbulent fluctuations, and we refer to that as the eddy term. And that eddy term has a mean component that it appears in the mean equations. So I will first of all just return to the full Navier-Stokes equation, well, the incompressible Navier-Stokes equations here, which I've written out in the in the flux form for momentum here, and that outer, that cross with the circle, this is the outer product. This is just a way of having vector time, vector tensor, and so on. And this is the continuous equations which we're trying to solve. At final resolution, we have to parameterize some terms. We do a Reynolds average on this equation, and you'll see that on the left-hand side we have a set of equations that looks very, reminiscent of the continuous equations, but each of these nonlinear terms, so that's the V outer product V and the V theta, I've missed out salinity here, those terms all lead, because they're products, nonlinear, they all have eddy terms. So this tensor here is known as the Reynolds stress tensor, and it has certain properties, certain symmetries. You might notice V prime U prime and U prime V prime are the same thing, so I've written it out here in a symmetric way, where there are 3 components off diagonal, which are equivalent to the opposite 3 components. And then we also have a turbulent heat flux, and there would be a turbulent salt flux, which have these, it's 3-dimensional. There's also an approximation sign here, because the equation of state is also nonlinear, and it's something we forget about. The equation of state is nonlinear, by definition, if you were trying to say what is the average density, it's not simply the equation of state with the mean fields inside it. That difference was actually pointed out by Brent Carr, and Ian Grooms down at CSU here has actually analyzed this, and with a student produced a correction to this equation of state, which leads to some significant terms when you have temperature variance below the grid scale. So this is the Navier-Stokes equations. This is very common. But now one thing to point out, the reason I went back to Navier-Stokes is all the equations we have will have the same so-called eddy terms appearing in them. There's always going to be a U prime, U prime, a U prime, V prime, and a U prime, theta prime, and so on. And it doesn't matter which process you're talking about, okay? This is process independent, these equations. It doesn't matter whether we're talking about Langmuir turbulence or convection or mesoscale eddies. Like these terms appear somewhat. The structure of those terms will be very specific to the process that we're trying to parameterize, but the appearance in these equations is independent. So I'm going to start off looking at the surface boundary layer, because that's basically how the ocean is driven from above by the atmosphere and the sun. Oh, sorry. I was looking at my future slide. Need to first of all, this is a side comment. And so one thing I didn't point out in the slide is I put time in square brackets for the Reynolds averaging on this slide. And in these equations, there's a d by dt of a theta bar and a d by dt of a v bar. But the bar, I said, was kind of quote unquote time mean. But if it was a time mean, there shouldn't be a time tendency. This is one of the inconsistencies that we sort of sweep under the rug when we're talking about Reynolds averaging. There is a better way to do this, which is to talk about ensemble averages, which is kind of ensembles of different realizations. So you've got turbulence, which is unpredictable. And you can say, well, the average of all those different ensembles is the same thing as the eddy term. But again, the question of whether the ensemble is evolving or not raises the question of whether the d by dt term is doing anything at all. So this is one of the kind of awkward definitions, awkward problems with the Reynolds average as we've defined it. There is a sort of more complete way of going about this, which is to take the view from the large eddy simulation field, where they don't take a mean, but they take a spatial filter. And this is very much more relevant to what we're actually trying to do, because after all, most of the processes that we're trying to parameterize are evolving on timescales which we can actually resolve in time, just not in space. So this is a more relevant approach, which is where you say, I'm going to decompose my continuous field, A, into a smooth, large-scale field, which I can resolve. That's the A tilde. And then the remaining part, which is the small-scale fluctuations. And we've labeled that with an A prime prime here. This is traditionally we use a prime prime for the anomaly here. And there is a slight gotcha with this approach, which is that there is no filter. And I've just given an example here of a Gaussian filter. There is no filter that can be perfectly designed such that a filter of A prime prime is 0. And so what that means is that we end up with these two terms, which in the Reynolds average disappeared. These two terms here will remain. They'll be small. There is going to be a correlation between the small scale fluctuations and the large scale. You think about it this way: you've got this large scale gradient over here, and you've got these fluctuations, and then if you look at the product, the stuff on the left-hand side where the field is lower is getting less weighting than the large scale than the stuff on the right-hand side with the larger values. So it's very, very hard to construct filters where these terms will be identically 0. People work hard on it, and you can make them smaller. But these two terms are referred to, when it's the momentum equations, referred to as the Leonard stress and the cross term. And there are parameterizations that actually focus on trying to parameterize these three components of the non-resolved flow or terms explicitly, independently and explicitly. We're not going to talk about that. We're just going to kind of make this leap of faith that there is a connection between the things we're parameterizing and the equations. And I mentioned this as a side comment because most of the parameterizations which we do talk don't even think about or make this distinction. So this is what I was going to say. So we're going to talk about, first of all, the ocean's surface boundary layer. So the atmosphere drives the ocean by wind stress, and there's radiation coming in from above, they're let through by the atmosphere, and so on. And then, of course, there's direct heat exchange, sensible heat and latent heat through evaporation. And what that does is it drives turbulence even through shear-driven turbulence, where the wind stress is dragging the flow in one direction, and then the shear is leading to instabilities, or convection, where you're taking out buoyancy and it's unstable and it overturns. So this is an example using ocean anagons I found on YouTube, Ali Ramadan's channel, where I'm showing on the left-hand side just the vertical motion, and on the right-hand side he's modeled phytoplankton or plankton of some form. I don't know which plankton. And it's just showing you that the scalars get transported around by these small-scale features. Remember, this is resolving the convection and the stress in this case, shear in this case. And this is all going to be very much smaller than the horizontal resolution of our circulation model. Horizontal resolution in particular, because we might actually be having the near equivalent vertical resolution, but that's a different issue. So that big, complicated, turbulent process driven from above is parameterized most famously by the K profile parameterization due to Large, which was written up by Large in 1994. And here we are. This is the aspect ratio of the problem means that the flux that we're most interested in is the vertical turbulent flux. And that's an aspect ratio problem. So at coarse horizontal resolution, let's say 1 kilometer, and let's say more typical resolution, the vertical of say 10 meters, the thing we're trying to parameterize is the vertical flux, because the horizontal component is such a small angle compared to the horizontal scale, right? So So we're looking at the vertical flux of in this case, scalars, a scalar, arbitrary scalar S, or salinity if you like, and that correlation between the vertical motions and your scalar are parameterized as a diffuse, with a diffusive component, down gradient. I think I might have missed a sign there. And then also a non-local component, which is parameterized by this gamma function. And in KPP, they use the same diffusivity. And this diffusivity and this non-local transport are going to be cast in terms of a non-dimensional coordinate, which is measured, basically a sigma coordinate between the surface, where sigma is 0, and the base of the mixed layer, which we'll define in a minute. So sigma goes from 0 to 1 in the mixed layer, and here's a plot of that going from 0 to 1 down here on the right, bottom right. The diffusivity is prescribed as a product of a length scale and a velocity scale. So diffusivity is measured in meters squared per second. So we have a length scale, which is going to be the boundary layer scale, the H, and then a velocity scale, which is this WS. And that's basically going to be a function that models the scale of this W prime, okay? And then there's going to be this big G function, which is a shape function, which turns out to be chosen, here is chosen to be a cubic function that has to match certain boundary conditions, and it gives rise to this cubic, where the gradient at the surface matches Monod-Novikov, and then comes back to 0 with no gradient at the bottom. So that's a cubic. The cubic is the simplest function that satisfies those boundary conditions. The theory that goes into these velocity scales is comes from, again, Monod-Novikov and some other law of the wall type theory, where the velocity scale is connected to the friction velocity U star. So U star is coming from the stress. And then the kappa here is the von Karman constant, which I will hope you know the value of. 0.4, did you say 0.4? Yeah? 0.4. There's also 0.42 and 0.38. Turns out it's not a constant. You know, we guess, typically we use 0.4 in that vicinity, but it turns out it's actually not a constant, which is one of the challenges here. But, you know, 0.4 is good enough for most of this theory. And then the boundary layer depth is defined by this relationship here, which is the Richardson number, which is the stratification, where B is the buoyancy reference, which is the BR here is the average buoyancy in the boundary layer, and B is the function of buoyancy as a function of depth, divided by the shear, which is the same form here, average velocity over the shear, the velocity is a function of depth. And this is a parameterization of velocity scales following this complicated rule up here, and I have no way of explaining that. I don't remember where that comes from. But this is basically the Richardson number, okay? And the idea is the boundary layer depth is going to be defined such that this Richardson number is equal to a critical Richardson number, which is a parameter that we will be setting. And so this defines, you work your way down the column, evaluating the bulk Richardson number, and at the point where it crosses this threshold, that's where you define the boundary layer depth to be. So this is most of everything. There is one last part, which is the non-local transport term, which is in KPP is cast to be a different coefficient times the same shape function, and then is matched at the surface to the buoyancy fluxes, or the fluxes of the scalar we're talking about. So now we have all of the terms in this closure at the top here defined, and this was kind of set the standard for boundary layer schemes. Before this, we were looking at bulk approaches like Krauss-Turner and so on. This is the kind of the standard for global climate scale boundary layer schemes. In MOM6, we actually haven't coded this up directly. We're actually using this via a package called CVMix, which was developed in collaboration between GFDL and NCAR. Mike Levy is not here today, but he's kind of the master of this repository. And so this code is imported into the model. We call it via one module in MOM6, but then it calls through to this package. And so I've got the links in the notes here. There'll be links to that module where we're calling it from, and then the actual repository itself, CVMix. And it's controlled via these flags here. We won't go through those in detail. So that's KPP. And I believe that most of your configurations are using KP. Is that right, Gustavo? Right, yeah. MOM6 actually has an alternative boundary layer, which we developed at GFDL. This is due to Brandon Reichel and Bob Hallberg. And this I'm not going to explain in as much detail as before, but it's basically uses many of the same principles, but with the big difference, which is it's using an energetic principle to define the, to close the problem and define the boundary layer depth. And so the idea here is that there's going to be a boundary, a balance between the mixing and the, which is the removal of energy and the production of mechanical and buoyant energy. And so there's this equation here, which is an integral form between the surface and the boundary layer depth. And rather than using a critical richness number criteria for the boundary layer depth, this equation defines that boundary layer depth. Where integrating down from the surface does this energetics add up? Basically, it gets to the point where it's equivalent to saying the boundary layer depth is that point at which all of the available turbulent energy has been used up. All the available turbulent energy from mixing has been used up. So this has a diffusive only component. There's no non-local part contribution in this parameterization. So this is not dissimilar to the KPP schema. It has a length scale and a velocity scale for the diffusivity. But it does use a different expression for the mixing lengths and the velocity scales. Although curiously, it still initially had a cubic function for the shape of diffusivity in the end. So this is just a comparison of this parameterization to different second order closure moment, kappa epsilon, k epsilon, sorry, and shows that the model is in terms of equilibrium is actually doing a good job. EPPL again has its own parameters. This time it's fully coded up in MOM6, but that is not in a package. Although we always meant to actually implement it in CVMix so that other people could use it, but it's one of those back burner projects which never makes any progress. So, okay, so that's the boundary layer. And then one thing about that large 1994 paper was actually a review of mixing in general. And although we all remember it as just providing a description of KPP, but in fact it has importantly also a description of the mixing below the mix layer. And that's to accommodate this sort of a process, which is shear-driven instabilities. So we saw this, there was actually happening in the mix layer as well, but below the mix layer, the idea is that if you have a stratified fluid with shears in it, resolved shears in this case, that will roll up the fluid in this Kelvin-Helmholtz type billows, which through static instability locally will lead to turbulence. And so you see this system of nice uniform roll-ups evolving into this turbulent system here on the right. So this is the shear-driven instability that is going to be parameterized. And here KPP took, on the left-hand side here, I'm showing the approach of describing large 94 again, large total 94, where it's again just a down gradient component with a diffusivity, which is a function of the Richardson number, again defined as this n squared. Now this is the local Richardson number now, not a bulk Richardson number. And so we've got n squared over the shear squared, and then there's this simple, well I say simple, it's a function that was written in a general form with an arbitrary power up here, but in practice they use this power 3. And so basically this function is 1 when the Richardson number is low, so i.e. giving you this strong diffusivity of order k kappa 0, and then above the, well above the critical Richardson number, you're using no diffusivity, okay? Again, MOM6, GFDL, they developed an alternative parameterization, and this is somewhat more sophisticated. It uses solves an elliptic equation for the diffusivity. So this is the double derivative of the diffusivity itself. And then there is a length scale which is used to add this Helmholtz term to this equation. And this is a function of the Richardson number on the right-hand side. So the source of this equation is a function of the Richardson number, which I've plotted here. And you see that this function also has a sort of critical Richardson number-like behavior in it, where it's finite or 0, depending on which side of the Richardson number, the value of Richardson number. The length scale is based on the kinetic energy, so the turbulent kinetic energy Q, and then there's these 3 different possible forms. It's either the distance from the boundary, which could be the bottom in this case, which is why this parameterization was developed, in fact, because it not only accommodates shear instability in the interior, but also shear for bottom boundary layer flows along the bottom, such as overflows. or it can be a balance, kinetic energy converted into a length scale via stratification or rotation. And then there is an equation, a vertical equation for the balance of, for the turbulent energy. And again, this is like a production dissipation type balance. So these equations are elliptic in the vertical, and they have to be solved implicitly because diffusivity and viscosity are fast processes potentially, so the time implicit, which means that this coupled system has to be solved in conjunction with the momentum equations. So this can be this is going to be an iterative and potentially expensive parameterization compared to the KPP form. But Bob Hallberg's brilliant at these things, and he's done some good optimization that it does actually solve in just a few steps. Again, we've got parameters to control these. I forgot what the KPP ones are, but these are just the link to the documentation will give you all the parameters you need. Okay, so that was the boundary layer. We did the shear mixing just below the boundary layer. But another aspect about the boundary layer is that we have these buoyancy gradients along it, and they tend to actually lead to instabilities themselves. And we call these mixed layer instabilities. So this is a simulation from Fox-Kemper, forget the year, it's on the next slide, Fox-Kemper 2008, and a series of papers thereafter, where they started with a strongly stratified fluid, and then force from above to give you this boundary layer, and then but there was a buoyancy gradient in the mixed layer, and that differential, but the lateral buoyancy gradient leads to instability, which you see starting to form here on the left. Now, after a finite amount of time, after say 10 days, those have evolved into larger eddies, and what their effect is to re-stratify the buoyancy in the mixed layer itself. Okay, there's also a bit of influence going on in the mix, at the base of the mixed layer, but primarily the idea here is what this buoyancy gradient you had in the horizontal did have vertical contours of buoyancy, and the effect of this instability is to slump those surfaces. So this is the process we're going to parameterize, and this is how it's done. The slumping process is inspired by, in fact, the Gentry-Williams parameterization, where there is a bolus transport, and the slumping is done by constructing a stream function that does that transport. And it's parameterized as a function of the mixed layer depth and the buoyancy gradient in the mixed layer, and also as a function of resolution. And then there's this shape function, which was found from the LES simulations, which is it's kind of a fourth order, it's quite a high order thing. It's kind of fairly constant and uniform. It matches 0 at the top and bottom. And this is the sort of stream function you get. In fact, this is the average stream function you got from those LES simulations on the previous slide. So this accounts for the circulation that requires, gives you that slumping. But it turns out that slumping is still happening on a subgrid scale. Those fronts are happening on the scale of the boundary layer up to, say, a kilometer or so. And the resolution of our climate models, which we're usually applying this method in, but even in coastal scales, you'll be wanting to use this. You need to, the buoyancy gradient that you measure at the coarse resolution is going to be far weaker than the buoyancy gradient that drove this process, which is on the frontal scale. So what they did in this series of papers is to upscale that buoyancy gradient. So there's a linear buoyancy gradient here. And they say, we're going to take that buoyancy gradient and we're going to basically just pretend that we're measuring it over the frontal scale rather than the grid scale. So there's this ratio here, which is the grid spacing over the frontal length. And that frontal length initially is sort of just set as a number. Say, let's choose 500 meters or something. And then your ratio, if you've got a 10 kilometer, let's do 5 kilometer because I can do that one. So then you multiply the buoyancy gradient by 10 and that upscales this transport, the circulation, and then that gives you the appropriate amount of slumping. So that's how the original Fox-Kemper scheme was constructed. And you'll see in the parameters for here, we have to set this length scale. In this case, I've chosen 500 meters. The problem is, in reality, that length scale is not a constant. It really should be a function of the boundary layer and whatever other environmental factors you have, Coriolis and so on. So we have, this is kind of like a first pass. And there was a subsequent paper by Abigail Bodner and et al., that actually developed a theory for that frontal length. And they did it by connecting to the processes that are actually driving the boundary layer. So again, here we have the friction velocity U star and now a buoyancy vertical velocity and W star. And so there's a theory that they use to get to a length scale from these parameters. And if you plug this length scale into the expression we had for the stream function, again with the upscaling, you get this expression here. And one point to note here is that some of the parameters that we saw in the last expression have moved place. And I didn't mention this, but if you go back here, the theory had a 1 over f dependence, but as we know, f goes to 0 on the equator, and so you can't really apply this expression in a global sense. And so there was this kind of hand-wavy idea, let's add in a time, that should be is an inverse timescale, 2f, in order to make sure we don't go to 0. So it's like, we'll just say there's always going to be this minimum timescale over which things are happening, or rate over which things are happening. And that's kind of very ad hoc, and it's purely an implementation choice. And different modelers made different choices about how to handle this problem. Now, the theory actually handles that. The length scale is now a function of f correctly, and the f moved from the bottom to the top. So now, this scheme actually goes to 0 at the equation. The stream function now goes to 0 on the equator. And this is actually great because the mixed layer is getting shallow there. Everything should be disappearing. So this is actually the right behavior we wanted. So now there's very much less ad hoc fixes from the implementation point of view. And the other thing that's changed here is now a cubic dependence on the boundary layer or mixed layer depth, whereas previously we had a quadratic, right? So this used to scale like h squared, and now it scales like h cubed, except we have two h's. And now so this parameterization actually distinguishes between the boundary layer scale, which is the active mixing part, and the effective mixed layer scale, which is the kind of longer time scale evolution of the system. If you try to diagnose the mixed layer from real data or from an ocean model, you'll see that position of where the fluid has gone from being very, very well homogenized to not is actually quite blurry. And that's actually one reason for this distinction being important. And one thing we did in the implementation of this was we found that if we use a density difference criteria, which was the traditional observational approach, there are parts of the ocean where this parameterization was unable to behave properly when we're using a density difference criteria. And this is actually well known in observations that you have to use different density criteria in different parts of the ocean. So there's been revisions of how to define mixed layer. For example, Brandon Michael has got an energetic definition, and there's also a French group that have been producing better definitions which are more globally relevant. In this case, we were thinking about how what this parameterization is trying to do, and we were realizing that there's a part that's missing here, which is effectively the timescales of evolution of the system. So if you look at the active mixing depth in many parts of the ocean, you'll see that it's actually evolving diurnally. So during the summer, during the nighttime, you've got typically cooling type behavior, which will be deepening the mixed layer because you're introducing negative buoyancy at the surface, unstable, so mixed down. But during the daytime, that cooling is turned into a warming, and so it's basically not driving convection, and if anything, is actually restratifying by warming the surface waters. So a plot of as a function of time of the boundary layer depth, the instantaneous active mixing depth, is varying on a diurnal timescale, but the evolution of this instability process was of order weeks. Remember, it went from day 5 to day 20 or whatever the times were, but it's weeks for the evolution of this instability. And if we were to apply this parameterization with the instantaneous boundary layer depth, it would keep turning off. But those instabilities are lasting longer than that. They're lasting the day. So the first thing we needed to do was actually time filter this instantaneous boundary depth into something that was not going to vanish every day. And so we basically do this. We do a time filter. So there's a time scale here, which we call the decaying time scale. And basically, this stops the boundary layer depth from retreating instantaneously when you turn from cooling to warming. And so it retains this depth, and if you set this to a order a day or a few days, it will filter out the diurnal cycle and give you something much more reminiscent of the kind of what has recently been actively mixing. But then there was a different length scale, which is the actual mixed layer depth, which is a longer time evolution. This is kind of closer to the density difference definition. And we use a second time scale, we call that the growing time scale, and we'll use a different time scale there. We'll make that, say, 10 days, or whatever you think is the most appropriate time scale for the length of this instability process to grow, and you use that as the boundary layer depth as well. So then you combine these together, you use the larger of these, and then that's how you do the same thing for mixed layer depth versus boundary layer depth. And this gives you something that lasts, but also has a finite response time. So you could start cooling, and these instabilities will grow at this rate, and then they will last long enough at this rate. And I think I got my timescales back to front when I was talking about it, but you get the idea, right? So you've now got two timescales which you can tune to give you the effect you want. We found that these timescales are actually leading order parameters, and that implies that if you're using the older approach of a density difference, that you would have a very strong sensitivity to the choices, and that's it's important to realize that these parameterizations are a combination of theory and some ad hoc implementations, always, where very often the ad hoc choices matter as much as the theory. Again, parameters and the documentation does exist. So, and I've shown you here some typical parameters that we use. So for this case, I've used, it looks like only a fraction of a day and then 10 days for the decay. Okay, so that's the mixed layer. Now we're going to move on to the Reynolds terms, the Reynolds stress terms. So it is, do you remember we talked about the Coriolis computational mode? The standard grid has these computational modes. You need to have some form of dissipation that selects those fine scales to dissipate those modes in this model. It's very hard to run this model without some sort of horizontal dissipation. And Smagorinsky had developed a theory for three-dimensional turbulence, which was scale invariant, meaning it applied at all parts of the spectrum where there is 3D turbulence. We take that idea and apply it only in 2 dimensions, okay? So this is a bit of a inconsistency because the theory was for 3-dimensional turbulence, but we're applying it primarily in 2 dimensions. There is an alternative theory, which I'm not going to describe, which is Leith, and there are some implementations of that, and also in combination with some of the mesoscale parameterizations. We call it QG-Leith, but I'm not going to talk about that. But this is the scheme that we tend to use because it's actually very effective at controlling the small scales in the flow field. The idea is that the stress tensor, now it's just horizontal two-dimensional, is a function of the tension and the strain in the fluid. And those are defined here. That says that there's 2 components to the stress, and they are proportional to the tension and the strain. Sorry. These are operators which are, if you've written down the equations and played them before, you'll notice that these look a bit like divergence of vorticity, but with the wrong signs. And these, this is just, coming out of fluid dynamics and the way that properties of the system. These are the invariant properties of the flow field. These stresses have factors of 2 in them, which are often missing in many notes. This is actually, I based this on Smith and McWilliams, who wrote a very comprehensive paper about anisotropic viscosity. And they, I think, correctly included these factors. And even though there's a cancellation between the half and the 2, which you'll see in the code, this is actually what the notes, our documentation, refer to. The key thing that Smagorinsky did was he sets this viscosity that relates the tension and strain to the stresses as a function of the tension and strain and the grid spacing. So dimensionally, this is giving you the 1 over time, because this is du dx and dv dx's and so on. So that gives you per second. And so the square root of per second squared is per second. And then you have the length scale here coming from the grid spacing. And the key property of this is that if you plug in this viscosity operator into the equations of motion, you say there's going to be a balance at the grid scale between the nonlinear advection and the dissipation, which is how we're going to, this is what we want when we want to control the noise at the grid scale. That gives you, this is what the grid Reynolds number is. So this expression here is a balance between advection and dissipation. The grid Reynolds number turns out to be the reciprocal of this coefficient here. So in other words, the Smagorinsky coefficient is the inverse of the grid Reynolds number. And the Reynolds number, if you want it to be smooth, means it needs to be relatively small, okay? High Reynolds number means very nonlinear, and that's when you're going to get lots of noise. So this is what we like about the scheme is like you can just say, okay, as a numericist, I just want the grid Reynolds number to be 10, and so you use 0.1. There are recommended values for this, and you can, of course, change this parameter. And if you do, one thing you'll find is that your solution depends very much on it. And this is a result from a large-scale model where we were trying to measure the spurious diffusion affected by the noise at the grid scale. And this is a plot of the results as a function of this grid Reynolds number. And you see that there's a strong behavior, marked behavior as a function of the grid Reynolds number. And you want to get to low grid cell Reynolds numbers in order to get nice smooth solutions that don't have artificial problems. The parameters, Smagorinsky is true, and then there's this coefficient. And in the documentation, we actually give recommended values for some of these. You want it to be a finite number so that the grid Reynolds number is not, say, above 10 ever. There is a paper by Steve Griffiths and Rob Hallberg in 2000 that took the Smagorinsky idea and then turned it into from Laplacian viscosity to biharmonic viscosity. And the argument about this was not physical, but purely numerical. We wanted a even more scale selective control on that grid scale noise. And so it's exactly the same idea. There is a two-dimensional Reynolds stress that we parameterize in terms of, well, stresses. And those stresses are now higher order derivatives of the tension and strain. So this expression here is now, if you take the divergence of this, you'll get a kind of del 4 type of U and del 4 of V. The viscosity now dimensionally has to be meters to the 4 per second. So you simply change this delta 2 to a delta 4. And there's a coefficient here. And then again, if you plug this in to a balance between this biharmonic dissipation and the nonlinear advection momentum, that'll give you a grid Reynolds number. And again, you have this parameter being the inverse of the grid cell Reynolds number. Again, there's no physical justification for this. It was really a requirement to try and control the grid scale noise. So this is purely motivated by numerics. And in high order simulations, we prefer this to the Laplacian operator. The Laplacian operator has been very widely used and is useful at coarse resolutions because it gives you resolvable boundary layers. And if you remember your Monk and Stommel theories, you need to have enough dissipation that they're a resolvable boundary layer where the eastward propagating Rossby waves are being dissipated fast enough. The Laplacian operator gives you that boundary layer scale, but if you use a biharmonic operator, it gets a bit too tight to work well, and so you won't get you'll get noise at the western boundaries. But at higher resolutions, the scale selectivity of the biharmonic operator is very much more preferred. And in fact, we turn off the Laplacian, very often turn off the Laplacian operator because it's not scale selective enough, and it damages the just above the grid scale part of the spectrum where you're trying to squeeze the most out of your numerical model. So we prefer the biharmonic operator for high resolution simulations. This is just a comparison. You can see how old this work is because it's all black and white contours, right? This is taken from that paper in 2000, just showing that I think this is relative vorticity. It's just higher amplitude activity when you switch from Laplacian to biharmonic. And the parameters again, turn on Smagorinsky, biharmonic, and set the coefficient. And this again, we've got the recommended range of parameters for the model. Okay, so staying with the Reynolds stress, there is an interesting, well, not interesting, I mean, it's just a function, it's a dynamical behavior that there is the transfer of, okay, I need to start this one over again, right? In quasi-geostrophic turbulence, there is a well-known odd behavior in contrast to three-dimensional turbulence, where there is an upscale transfer of kinetic energy. in three-dimensional turbulence, energy and entropy are cascading downward where they're dissipated, right? Downward meaning to smaller and smaller scales. So you have all this three-dimensional stuff going on, and it's driving small shears and smaller eddies. Remember, there's that rhyme about big eddies have smaller eddies, etc. So there's a cascade of energy and entropy to small scales. But in two-dimensional turbulence, this weird, interesting phenomena where there's actually an upscale to larger scales transfer of kinetic energy. And that is a problem for models with finite resolution, because what it means is your model should be seeing a generation of energy from the unresolved part, right? And that's pretty hard to do. This paper by Janssen et al. Proposed an interesting idea, which is to at least compensate for the energy that we're taking out via the dissipation. And so we sometimes interpret this as putting energy back in from the unresolved part, but in really what it's actually doing is compensating for the energy you took out explicitly by the dissipation, because we know that instead of dissipating at small scales, we should be seeing upscales. Now, you still need the dissipation because you need that entropy cascade, so you need to be taking out entropy. But the way that they did this was they kept both the Laplacian and the biharmonic operators. The biharmonic will be this grid scale numerical dissipation needed for removing entropy and keeping the model stable. But then we're going to monitor the implied subgrid scale kinetic energy. And that implied subgrid scale kinetic energy is going to be increasing when you have dissipation, right? So the large scale flow is losing energy, the hidden subgrid scale kinetic energy is gaining energy, right? And then what they do is they say, well, if we had a Laplacian operator, which would normally be dissipative, if we change the sign of that viscosity to negative, it will be injecting energy, right? And by the way, when I first saw the idea of using negative viscosity, I kind of had a heart attack, because that's unconditionally unstable. It's a very weird thing to do, but as long as you don't make this term, as long as you keep this term smaller in amplitude than this term, it will be stable because this is a stabilizing term, okay? So you could choose a negative viscosity to turn what would otherwise be dissipation into a source of energy for the large scale, which means that this term is now a sink of the subgrid scale energy. So source, sink, okay? And the only thing you want to do then is say, well, obviously, the subgrid scale kinetic energy should be a positive quantity. If it goes negative, nothing's happening. So what you do is you parameterize this backscatter viscosity as the negative value, but you clip it to be 0 or negative, right? That is how this and by the way, this equation is actually referred to as the Meeke equation, but there's borrowing bits of code there. But this idea of, say, let's just compensate for the energy that we're losing by putting it back in at larger scales because it's a lower order operator, does amazing things. So here we are on the right-hand side. I'm showing a spectrum, eddy kinetic energy spectrum from a high-resolution 3-kilometer model. It's a channel configuration with topography. I forget the details, but there's a high-resolution, but let's call it a well-resolved simulation, which has this K-3 spectrum. And then there was a sequence of coarser resolutions, 10-kilometer and 20-kilometer in blue and orange here. And without this backscatter term, you'll see that we are unable to get the right amount of resolved energy at the resolved scales. And remember, this is the grid scale over here in these models. And these are very well resolved. This is much larger than the grid scale. And so you would hope that those scales are doing well, but they're not because we haven't got that upscale transfer energy. By injecting the energy we're taking out in dissipation at these scales here, we were able to move these solid blue lines and orange lines to the dashed lines. You see that they can very well match in the well-resolved part of the spectrum. I mean, it's a huge success, right? Great, that's a great thing. This is called the backscatter, and this is due to Janssen et al. In 2015. And parameters again. I haven't got a link to the documentation, which probably means it's not documented. Kate, we'll have to fix that one. Yeah, it might be there, but I was checking for links. So, okay, so that idea, that concept, was primarily about compensating for over dissipation in the model, because dissipation of kinetic energy shouldn't be happening. Okay, but it's not actually injecting energy from scales smaller in reality, because all it's doing is diagnosing what we're actually taking out from the large scale is not actually a parameterization of what's going on for a small scale. There's a recent paper, it's just come out, which was to say, why don't we actually try and parameterize those Reynolds stresses to actually put in that backscatter from the unresolved scales. So what Parameterizations did was he took the 10th of a degree CM2.6 model, which is a couple model from GFDL from a while back. It was in the history of MOM6 slide from yesterday. And they diagnosed the difference between the resolved and total full stresses here, which is not, I'm deliberately not using the prime notation here because he actually did the LES scale filtering. So this is truly now the LES type term. And so those three terms which remain when you do the LES type filtering, they are the difference between the true filtered product and the product of the filtered, right? So this has now got all of the terms. So he diagnoses the horizontal stress that is apparent in the CM2.6 data, and he builds a neural network that can model this. One of the most important things about this paper is he figured out how to build a network that was generalizable. And he used something which I think you all learned about when you were probably at high school, maybe undergraduate, Buckingham Pi theorem, right? Do you all, I'm looking at funny, Buckingham Pi theorem is about looking at the dimensions of your phase space in terms of parameters. It says basically when you have various length scales, time scales, velocity scales, and so on, there's only so many ways you can combine things into non-dimensional parameters. One way to look at it. What he found was that if he applied Buckingham Pi theorem, first of all, the neural network that he was training had to have non-dimensionalized inputs, and the non-dimensionalization of that could in fact be quite arbitrary. So in this case, he's taken an input vector x, which is not defined here. Oh, so it is, yeah. Input vector x, which is a function of those stresses and strains, and in fact also vorticity, and a 3x3 stencil, so with 9 points per variable. So this is like 3 times 9 is 27 length vector. And if you simply normalize that vector, take that vector norm, and non-dimensionalize that way, that's a choice for how to non-dimensionalize, but it's sufficient under Buckingham Pi. If you make the ANN a function of that, then all you have to do is re-dimensionalize the output appropriately, and the length scale does have are the grid scale and the normalization that you had here. And this parameterization was trained on CM2.6. Okay, so it was trained on a global model, but then evaluated in many different contexts and at different resolutions. And so here we are, we're diagnosing the upscale kinetic energy transfer from a 32nd degree Neverworld-2 model. This is a model that the CPT project developed. And then parameterize it at a coarser resolution using this ANN. And you'll see that this is a remarkable coincidence. Not coincidence, correlation, I should say. It's not a coincidence at all. It wasn't designed to do this. And just to drive things home, I can compare this to the previous backscatter approach. So here we are. This is a model that we're currently developing at GFDL 5. And we have this long-standing bias in the North Atlantic where the Gulf Stream doesn't separate early enough, and there's this warm bias on the northern flank of the Gulf Stream, and then we have this blue spot. It's known as the blue spot of death in climate models. And most models have this, and it's associated often with a weak AMOC. And if we apply the Janssen et al. Parameterization where we're putting in a compensation for the dissipation that we're using with the grid scale, which was done here by Jenny Chang et al., we see that there is a difference, there is a response, and we were very happy. But when we used to present this work, we used to show the difference because you could see something. But showing the total bias, you can hardly see the response, right? But Pavel Parameterizations' approach, using the data-driven machine learning parameterization, is able, for the first time ever, actually lead to a change in this bias. We've actually changed this bias from red everywhere to pluses and minuses, pretty much small-scale noise at this point. And this big blue spot of death is nada, it's gone. So this is huge. I mean, however, I said earlier on, normally our parameterizations are a combination of theory and data, and this is an example where we just took the data, built a parameterization, and we think we know what it's doing, which is the backscatter of energy, but it's actually doing everything. It's doing all of whatever was in those. I shouldn't call them mental stresses, but whatever was in those stresses that was the difference between the small scale and the large scale. Everything that's the difference was now parameterized. We don't know whether to call it just backscatter. It could be something else. And in fact, Pavel makes a point that it's actually doing some dissipation. Sometimes it does some dissipation as needed. He's finding that it changes the solution, and the best thing to do is to, yes, it's sensitive to that. And he's using a much weaker much lower level of Smagnitsky, which is something I wouldn't normally advise, but that's indicative that this is doing some dissipation too. Okay, so that is so this can be turned on the parameter with parameters. This is based on the paper by Zenham and Bolton, which are trying to model, also using machine learning, model as backscatter or stress term, based on a bit of combination of theory and different kind of machine learning. But in this case, it's just a neural network, and you turn it on, and you provide a file with weights. The reason I'm dwelling on this is, do you remember I said at the beginning when I showed you the Reynolds average, Navier-Stokes, and I said all processes are represented with the same eddy terms, right? It doesn't matter which process you're looking at, it's going to have to be reflected in one of those eddy terms, and all processes are hidden inside those. There's a possibility now that we could actually just code up a network for each of those eddy terms in the model and never have anybody who's worried about parameterization go to the code again. All they have to do is provide those weights for the modelers to use. There's just an interesting possibility there. Anyway, that might be the future, who knows? So that's everything I have, and I actually ended on time today with 3 minutes to spare, so. Well, I do think that covered pretty much everything you might consider using at global scale, at coastal scale resolutions. I did say I have got some slides on Jennifer Williams, which is, as I said, something that you would use at large scale, but I don't think that's appropriate to use at low resolutions. There are plenty of other parameterizations such as bottom drag and many other things, but these are the kind of the big ones that you need to know about. You'll need to tune them, or somebody has tuned them for you. Questions?
Yeah. Yeah, a very good talk. So the first question is whether MOM6 models support LES.
I personally don't think you should consider it an LES model. We did, as Gustavo and I were talking about yesterday, the Smagnitsky closure itself is actually an LES closure. But it's like today in CFD, it's like the first one you try, but there's higher, more sophisticated ones that people prefer. So that is an LES closure, but otherwise I would say, apart from this backscatter, driven backscatter, I would say that most of the parameters are not strictly LES model closures. So there is no reason to say that we couldn't add them, but remember that the model is also hydrostatic. So if you're trying to get into resolving overturning processes at coastal scales, then it wouldn't be the right model to choose. Not yet. We'll be talking about hydrostatic, but yeah.
And my second question relates to the viscosity. So you mentioned how to calculate viscosity in KPP scheme or some other scheme. Yeah, but I know usually people use the calculated viscosity to like the same value as a diffusion coefficient. That's
the Prandtl number, yeah.
Yeah. So yeah, how do you think that?
So we currently most parameterizations do have associated with them a Prandtl number, and for reasons we have no idea. Sometimes that Prandtl number defaults to 0, which is a bit awkward because obviously it shouldn't be. So that's been changed recently, and we've also tried to separate the Prandtl number for each of the individual parameterizations, so you have a bit of control over this. But it is a constant, and there's plenty of suggestions that it should actually be not constant and something else, depending on the process. So there's room for adding things there as well. But for the most part, there are these constant parameters which are identified with each parameterization, which gives you that control.
And my third question related to Baylor's scheme.
Yeah.
So he used the damping filter to damp out the dyno signal.
Yeah.
But LC coupling process like MGO definitely has very strong dyno variability. So if you use the damping filter there, whether will change the coupling.
Yeah, I agree.
thing.
I totally agree. As I said, it's one of every parameterization always has an ad hoc component due to the implementation. That was this version. But previously, before we did that filter, it was adding this timescale tau, right? So it's like these parameterizations are encapsulated in our best understanding, but our understanding is incomplete. Let's put that question.
Yeah, I still have some questions, but I will discuss it later.
Seems rather full. Yeah.
In terms of the code realization, if you want to use neighboring stencils, like in a lateral way, what's the number of stencils you can use maximum, like versus the performance drop? What does that?
Well, that's an interesting question. So basically, that's the wider the stencil, for example, comparing the passing to button mode, the more expensive it becomes. Because you're just loading up more values. There's in the hardware side, you're using more memory, and the memory bandwidth is an issue. So the wider the stencil, the more expensive it's going to become just because of the number of values you're loading up. In the context of machine learning, which I think is partly what you're asking about, right? The wider the stencil, the more computation you're going to do as well, because you're going to have all those weights multiplying those channels and those channels being manipulated and so on. So the cost of a network and the scales, I'm assuming at least as n squared, if not more, where n is the number of points in a stencil, not the width, but the number of points. So it gets very expensive very quickly, which matters for CPUs, maybe not for GPUs, because they're good at this kind of machine learning type operation. But as a general rule, that the more values you're using, the more expensive it's going to be. I don't know where the crossover is in terms of significance. It's one of those things that's been trial and error. You have to try, and if it becomes too expensive, it won't get used until you figure out how to make it smaller.
But in principle, there's nothing stopping.
The code, there is in principle no limit in principle, but in practice, the upper limit will be the size of your processing element in parallelization. We typically use the most efficient, at least on CPUs, is typical to use at least 20 by 20 points, if not more. And if you have a stencil that's needing more than 20 points, I'm a bit worried about parameterization. It's becoming kind of global at that scale, it's a bit more like an emulator rather than a parameterization.
Time for one more question.
Please, KPP also apply to the ball boundary layer?
It has been done in other models. I don't think it has been done in MOM, but the EPPL has recently been turned into a bottom boundary layer. I think, actually, in Sega Mix, has it been applied? Mike isn't here. Does anyone know if Sega Mix has it upside down? It should be done, right? It should be done because the bottom boundary layer is a boundary layer with turbulence, and right now modeling it as just this bulk scheme where you just have an enhanced diffusion, which is what we do. The energy taken out by the quadratic drag is turned into energy for mixing, where we just set a higher diffusivity. That's the very crude model, and so applying KBP would be the right thing to do. EPPL was applied upside down for that exact reason, but if you want to use KBP, then it needs to be implemented. You need to get somebody onto that. Who's volunteering? Okay, I think it's 5 past. We need to have coffee. Thank you very much.